Okay, good morning, good afternoon, or good evening to all. My name is Maria Luisa Toledo from the Brazilian Institute of Geography and Statistics from Brazil. And I'm also from the UN Regional Hub for Big Data in Brazil. And today it's a great honor to welcome you all to our webinar on Earth observation and artificial intelligence for agricultural statistics, which is organized in partnership with the UN-CEBD Task Team on Earth observation and the FAO, the Food and Agriculture Organization of the United Nations. This is the 8th session in our ongoing webinar series on climate change indicators. We'd like to inform all participants that the webinar is being recorded and will be shared with the community afterwards. And it's important to say that this webinar is part of a broader in-person workshop we are hosting this week in Rio de Janeiro, where we've gathered a group of outstanding experts to collaborate on the United Nations Handbook on Remote Sensing for Agricultural Statistics, which is a key resource to support the National Statistical Offices in using Earth observation data for agriculture monitoring and analysis. And I'd like to express my sincere thanks to these experts who have generously taken time out of their schedule here in the meetings in Rio de Janeiro to offer this two-part webinar series for the broader Latin American and Caribbean community, which is supported by the Regional Hub. And in fact, today's session can be seen as a continuation of the discussions led by these same experts during the workshop they offered for the Hub back in April. That session was recorded and is available in our website. And today we are going to talk about Earth observation monitoring and supervised artificial intelligence for crop mapping. And to open our session, I'd like now to invite Mr. Lorenzo De Simone, which is the technical advisor at the Agri-Food Economics and Policy Division of the Food and Agriculture Organization of the United Nations. Lorenzo, thank you very much for being with us, and the floor is yours.
Thank you very much, Maria. Good morning, everyone. It's a pleasure to welcome you to this webinar, jointly organized by IBG, which is the host of the UN Regional Big Data Hub for the Latin American and the Caribbean, and of course, in collaboration with the FAO. Let me begin by thanking IBG for its outstanding leadership in the data innovation and its strategic role in strengthening regional capacity for data-driven decision-making. So this event, as Maria anticipated, is part of the work of the UN Committee on Experts on Big Data and Data Science for Official Statistics, UN-CEBD, and specifically its task team on Earth observations, which I have the honor to lead together with INEGI Mexico. Regional hubs like IBGE and also the global hub in China, they form the backbone of this initiative, which is enabling national statistics offices to harness Earth observation data, artificial intelligence, and other non-traditional data sources in support of the 2030 Agenda and the statistical reporting requirements. This workshop is a practical example on how these hubs, they bridge together global knowledge with regional applications. Of course, FAOS, through its Agri-Food Policy Division and also the Statistics Division and international partnership, works together to bring EO and I into the heart of agricultural statistics, not as futuristic vision, but as real scalable tools and that NSOs can use. So we're deeply committed to capacity development and to ensuring that these tools work in practice for yield monitoring, crop mapping, and more integrated policy planning. So a key ambition of this event is to foster integration between geospatial and statistical communities. Earth observation data alone, in fact, is not enough. It needs to be combined with survey data, ground truth, and statistical frameworks to become actionable information. This is why we're also working collectively on the UN Handbook on Remote Sensing for Agricultural Statistics as a key deliverable of this workshop week. And today's focus of this workshop is really on Earth observation and supervised AI for crop monitoring with sessions from GeoGlam, European Space Agency, VITO, and country experiences from Mexico and Brazil. Whereas tomorrow's agenda will shift to statistical integration and time series Earth observation geoprocessing, including crop area estimation using regression models, the role of global geospatial statistical framework presented by Claudio Stenner from IBGE. And then we will have also a practical demonstration of satellite image time series, SITS, processing by Gilberto Camara. We will also hear from our colleagues in China on the use cases and handbook contributions before closing with a forward-looking panel discussions. So finally, this is more than a technical agenda. It's really about modernizing how we produce, we integrate and use agricultural data, especially in the global south. So let's make the best of this opportunity to share, learn, and collaborate. And thank you again to IBG and to all participants. The floor is yours again, Maria. Thank you.
Thank you very much, Lorenzo. And now we're pleased to welcome Mr. Sven Gillians. Sven is the Program Director of the GEO Global Agriculture Monitoring Initiative, the GeoGlam, where he leads international efforts to improve agriculture monitoring throughout the effective use of Earth observation data. Mr. Gillians has a background in agricultural engineer from KU Leuven, and he brings over 20 years of experience in remote sensing applied to agriculture. And prior to GeoGlam, he held various leadership roles at VITO's remote sensing unit, where he led projects ranging from global crop mapping to precision farming. Sven, thank you for joining us, and the floor is yours.
Thank you, Maria. Thank you for that kind introduction. Let me see if I can share my screen. This one. Is it now in presenter mode?
Yes, it's perfect.
Okay, good. So good morning, everybody. I guess most of the people are in the morning, except for a couple of the speakers. So my name is Sven Gillians. I'm the program director of GeoGlam, and in the next 20 minutes, I'll try to give you an overview of what GeoGlam does and how we're connected with the work that Lorenzo in the introduction just gave. So GeoGlam is a flagship program of GEO. GEO is the group on Earth observation. We started in 2011 with a mandate of the Ministries of Agriculture of the G20. That was raised after 2 food price spikes, one in 28-29 and one in 2010-2011, where the Ministries of Agriculture said that we needed to have increased global market transparency. We use remote sensing to provide information, timely, relevant, and actionable information to support market transparency. That was our first mandate. That's how we started. We're actually an international open community of practice of people working together and working with Earth observation for agricultural monitoring in different domains, amongst others also statistical frameworks or support to statistical frameworks. Then, if I look at what GeoGlam is and what we do, I try to get that in a schedule to get some of the working groups out. So on the left side of the slide, you see some of our drivers. The policy drivers in this case are two: food security, climate. SDGs are one. There's other conventions that drive GeoGlam, and for those things we develop products. In the food security, we have crop monitors are the main products there. We have an early warning part on focusing on food security. We have a market part on global food producers. We provide that information to AMIS, and they use it to predict food prices, to predict or to use that product in prediction of food prices and stability of the market. In climate, we have mitigation and adaptation. Those products, of course, they're not 100% addressed to all the user needs. So those needs feed into our R&D part, which is the top left part of the slide, where you have the essential agricultural variables. I'll come back to those later. Those are really the drivers of the research. JChem is in there, also mention that later. All that we try to use as much as possible open source, open data that is all stored in a geo knowledge hub. We do lots of in situ data coordination, and all those mixed together, we come up with information products, and those are then in co-design and co-development, then feedback to national and international organizations who actually use the product. So that's GeoGlam in a nutshell. I can't present GeoGlam without talking about the crop monitors. I'll go into detail in the next slide, but it's basically a global overview of crop conditions at different stages in the season. It's people coming together. It's over 40 experts in monthly conference calls that actually look at their EO data, look at their analysis, and come up with crop condition consensus-based reports. So you have to understand that the maps that you're looking at, so the top map, is not an EO-based product. It's an interpretation of Earth observation data coming from different organizations like FAO, like NASA Harvest, like the European Commission, GRC, different projects from ESA. All these people come together, the Chinese Crop Watch, they come together and they look at their data, they look at the different countries, they look at, and there's a discussion on the results. So 3 products: AMIS, the early warning, and then the global one. AMIS is the oldest one. It started really after the start of GeoGlam, where our first mandate was. So AMIS is the Agricultural Monitoring Information System, Agricultural Market Information System, with the headquarters based at FAO. The blue parts you see there are the countries that are being monitored. It's dedicated to wheat, maize, soybean, and rice, and it covers around 95% of the global market. If we then dive a bit into detail there, so these are the countries. In Latin America, you have Argentina and Brazil as very big producers. So this is from April this year, end of April this year, the condition, where you get an explanation on the colors. So the blue is exceptional, green is favorable, yellow is watch and poor and out of season. And then you get codes for the different crops. Again, this is people coming together and explaining what they see in their EO data, and then the report is written on a monthly basis. This is for the maize condition, so we do it for every, so you have the general overview, and we also do it for the different crop types that are important for the AMIS people. Then you get details also on percentages of in countries and also where in the season you are. Similar thing for early warning. It started only 3 years later. They look at different crops. The crops are here: maize, sorghum, millet, wheat, beans, teff, and rice, also different seasons. And it's completely different countries that we're looking at. Mostly in Africa, so I don't want to spend too much time on this part. It's a similar process, but it's much more where the aim is more national institutes are involved. This is where more regional and global institutes are involved in doing the analysis. And then we also have this crop monitoring tool, which helps you go into detail and zoom in and zoom out of the system. That's something that started a couple of years ago, and it's now being fully operational. All that work needs to be supported by lots of research, and that's where the essential agricultural variables come in. Essential agricultural variables is something that started in 2018. Last 3 weeks ago, we had a workshop at the Joint Research Center in Italy, in Ispra, bringing together the group to look at what is the evolution there, what is going on, and how do we proceed. So essential agricultural variables, they're really the key building blocks to produce relevant and timely information. So on the one hand side, you have policy, where you need to be able to monitor stuff. And on the bottom line, you have data. And the essential agricultural variables are actually the bridge in between those two things. Like if there's a new policy coming out, like the EUDR, so what is the data that we need to really monitor that policy? Do we have that data? And also looking at the data, which data can actually support different monitoring, different policy programs. We have in total 66 variables. This is a very complex slide. It's just to give you an overview of what is in there. Don't spend any time on I will not spend any time on going into details. You can read the slide horizontally and vertically. You have binary land use variables, which are spatially explicit. You have categorical variables, spatially explicit. You have continuous variables, spatially and non-spatially, and then the different levels at the horizontal scale as well. We have 66 variables, which is a huge task. And I think if we spent 3 weeks ago with the 40 experts we had in the room, we could have come up with at least 100. What is really important here is the link with EO. So it's not pure essential agricultural variables. It's really dedicated to GeoGLAM's mandate and what is measurable and what is observable with Earth observation. Those are really key boundaries of what we do. So what we're doing now is during that week, we selected a couple of them. So crop type, crop yield, forecast and estimation, irrigated cropland, evapotranspiration, field boundaries, and then land management. And we're going to do a gap analysis and also a stock take to see which products are available and where are the difficulties, where are the big gaps, so that we can, on the one hand side, talk to policymakers, on the other hand, also talk to some of the data providers. This is an old slide, but this is a typical output of also the essential variables work, where we look at the different products that are key for GeoGLAM, and we look at the different EO-based data sets that are available, preferably the open and free data. So I'm thinking about the NASA, the ESA work, some of the Chinese data sets, some of the data sets from India. What is available and how can they be used to produce those products? And also the most important one is, where are the gaps? This data set was back in time used also by ESA to support the ask to their member states on the thermal mission, on the LSTM mission that is going to hopefully be launched in 2028, 29. But we want to do that with the new analyzers that we're doing, with the new sensors that are coming up. where are still the gaps, where are the needs, and then we have, like with the whole agricultural Earth observation community, we can reach out to these organizations to request for new data, new sensors, more temporal frequency, higher spatial resolution, etc. Of course, and I think Lorenzo mentioned it at the start, EO data is not the only thing that we need. We also need a big effort in situ data, and the in situ data might even be harder than the EO data that we're getting. So one of the things that we try to do within GeoGLAM is as well in situ data coordination. A big part, and I think it's going to be in later presentations, is the ESA World Serial. They did a big part on in situ data for crop type mapping. This is an overview of what they have. Basically, we want to build a harmonized and qualitative data set where we can test, calibrate, and validate different algorithms. Zoom into the data sets that are currently, I'm not sure if that's 100% updated, this slide. People from World Serial and people from ESA might correct me on this one. But given the fact that we have lots of people from Latin America in here, if you compare different continents, there might be a small effort or maybe an exercise what data can be shared and what not, and how to share it. There's lots of discussion about privacy as well, but it's just showing the different amount of data sets that are being shared on different continents. What we also do is within our community, we look at who's doing what work where in the world, and of course, in situ data collection is a big effort. And if people know who is collecting where, people can work together and share data sets and combine things so that we get full coverage of a certain country, etc. Getting that out there and having people working together is one of the key things also that GeoGLAM does. And I think I'm almost there. Finally, JCAM, it's a global network of voluntary research sites where we do cross-site experiments. The good thing here is that if you have an algorithm that you want to test from, just say, field boundaries, how would that work in different agroecological zones in different regions of the world? And you can use that network to actually calibrate and validate some of your work. Different experiments have been done, and there's a couple of them coming up. Also there, it's open and free. You can just join the network by reaching out to the leads. And if you want to know the name of the leads, just ask, I will provide. So this is an overview. There's already a couple of them in South America. Some of the assets why you would join the JCAM network if you have an agricultural site where you're doing experiments or testing on. Then, of course, capacity building. We have open source documents freely available where we discuss best practices in the use of Earth observation for agricultural monitoring, but also, in this case, how to best approach certain training events. The last big training that we did was in East Africa. We brought 13 countries together in Kenya. The focus was on the crop monitors and the national crop monitors. So we had experts from these different countries talk together and see what worked in their countries, where the problems were. If these countries had the same problems, had the same gaps, had the same needs, we came up with documents covering these gaps and needs. And with those documents, they can go to stakeholders and to the donor community to ask for project funding to develop these national crop monitors in their countries. Of course, that work cannot be done without sponsors, and we got sponsoring from the UK Foreign Affairs and the World Bank, and also from ICPAC and GeoGLAM itself. And finally, all that information is stored in the Geo Knowledge Hub. where you can find the GeoGlam community. We have different webinars. All the software tools that are being used by partners are also available there with training material and use cases to test them. And then finally, some concluding thoughts. The challenges for food security will only increase with climate extremes, pests and diseases, but also conflict. We all saw what happened in Ukraine and the impact on global food prices, but also on the global market. Earth observation will play an even more important role in policy and in programs, also for, I think, also for statistical support. So we need to make sure that everything that we developed has a long-term continuity, so no one-off shots. Really, we have to work together with statistical agencies, with users in country to develop systems and to develop solutions that are actually sustainable for those countries and where countries can build upon. So that's why we need co-development. And then I think we also need to better integration between sectors and different science domains. And if you want to reach out, these are the contacts for GeoGlam. And with that, I give the floor back to Maria. Thank you very much.
Thank you very much, Sven, for the great presentation. It's very interesting to see your projects, especially this project on Africa, the Africa Crop Monitoring Learning Exchange, with so many important supporters like the World Bank. I think these initiatives, we are also having similar initiatives in Latin America and Caribbean with like supporters as Paris 21, the GPSDD. So it's very, very important. And I would like to ask the webinars you have mentioned at the end of the presentation. I'm not sure if they have been recorded. Could you please share the access link in the chat? So if participants would like to access, I think they would be very interested.
Yep. No, they're recorded. So that's what it's. That's if you, I'll share the link with the Geo Knowledge Hub GeoGlam community in the chat, and that's where all those webinars, they're recorded. So that's on different tools and that are being used, but also on how to write project proposals, and yeah, the tools themselves, training materials for the tools. It's all there. So I'll put that in the chat just now. There was also a link in my presentation. I'll put it in the chat.
Okay. Thank you very much, and congratulations for the work at GeoGlam.
Thank you.
I added a message to the chat. If there is anyone that would like to make a question, you can put it on the chat, or you can like raise your hand so we can open the microphone for participating. So feel free to participate, okay? And I think we can move forward to our next presenter, Mr. Zoltan. Our next speaker is Mr. Zoltan Santoy. Mr. Zolt, he's a land application scientist at the European Space Agency and is a professor at Stellenbosch University's Department of Geography and Environmental Studies. Mr. Zolt holds a PhD in geomatics from the University of Florida, and his current research focuses on global scale crop detection and yield estimation, early detection of crop diseases, and monitoring of key agriculture systems using Earth observation and AI. He applies advanced machine learning and time series analysis to improve agriculture monitoring, particularly in support of food security and climate resilience. Zolt also leads the European Space Agency Earth Observation Africa initiative, fostering the African-European R&D partnerships in agriculture and water resource management. Mr. Zolt, welcome. Thank you for being with us, and the floor is yours.
That was quite an extensive introduction, Maria. Thank you very much. Good morning, everyone. Muy buenos dias. I'm very happy to be here. Well, I'm physically in Rio, so as Maria introduced, we all came for the whole week for the workshop in general on the handbook, and of course, we were all looking forward to this webinar. Thank you again. Very welcome, everyone. And yeah, I think I have a lot to say, so maybe I just jump into the presentation. Just give me a second. And this is the one. I will put it on full screen. You guys see it? Very good.
Yes, very good.
So I was asked from the organizers, Maria, and of course from Lorenzo, to talk a little bit about where I am coming from, the European Space Agency, and of course try to focus on Earth observation and the infrastructure we provide, and put extra emphasis on crop mapping, which is the work I do anyway. So my name is Zoltán Szantói. I'm a land application scientist at ESA. But indeed, as you mentioned, Maria, I'm also a professor at Stellenbosch University. But I will focus here on ESA quite a bit, actually, what we do, where we do, how we do, and just I'm pretty sure everyone heard about ESA, but in any case, someone didn't. So we are mainly a European member state-based organization. We have 23 member states. You see all the flags in the bottom. Although you will see, for example, the Canadian flag. So Canada is a so-called associate member, so they are basically part of ESA as well, but not with a full membership. We have around 6,000 total workforce, and the HQ, the headquarters, is in Paris. But as you can see, the European spaceport on the bottom of the slide, so we are definitely present in South America. So in French Guiana is our spaceport where we send our satellites up, and more about that later. I am coming from the ESA Esrin site. You see it with the little red circle, which is basically, it's in Rome, Italy. And that's the site where we really focus on ESA's Earth observation activities. You can see that our yearly budget is around 7.7 billion for 2025. And I just thought to show these slides quickly, not to go into details, but to really show how ESA sees Earth observation as an important part of our activities. So you see that basically over 30% of our total budget goes into Earth observation. So the importance is very big. Our member states really looking into how to strengthen their Earth observation capabilities from both sides, building satellites, launching them, and of course, dealing with the data. And I will show some examples about both. And so here is the past, current, and future lineup of our satellites. But you have to realize here that we have three big groups of satellites: science, Copernicus, and meteorology. Science is generally short-term missions. Well, short-term still means 3, 4, 5 years of flying time of each of those satellites that you see there. The Copernicus mission is what we call an operational mission. Operational in a sense that the long-term availability of the data from these satellites are guaranteed. So just as an example, hopefully most of you heard about Sentinel-2, one of the workhorses of the Copernicus program. That's an optical satellite, 10-meter spatial resolution. Currently, 3 are flying, and they are providing data since 2014, if I'm not wrong with the exact date. And this data flow, and of course the satellites, will be continuing for the, well, kind of unforeseen future. So it's gonna go up for many years, and I will say a few more words about that later. And we have the meteorological satellites where we are supporting EUMETSAT, and again, we build all the meteorological satellites for EUMETSAT and what they use for weather prediction, basically. Definitely in Europe, if you see a weather forecast on TV, most of the data is coming from those satellites. Now, I talk about what we send up from French Guiana. So actually, the two first examples on this slide is the EarthCare and the FISA-2 satellites. Those were relatively small ones. We send them up with the Falcon 9 rockets, which are not ESA rockets. But when we are looking at a little more heavy-duty need, then we use our so-called Vega rockets, which are leaving the Earth from the French Guiana base, so from actually South America. So last year we sent up Sentinel-2C. I just said that there are 3 Sentinel-2s flying now, so A, B, C. And we also sent up Sentinel-1C, so third in each of these series. Sentinel-1 is, of course, a radar satellite. From there, only 2 are flying because one got a technical problem. So it's only 1B and C which are flying currently. So these were the launches we did, among others, but these are the bigger launches what we did last year. Talking about this year, some satellites were already launched, like the biomass satellite. I think, Maria, I think we discussed this earlier this week, the biomass satellite, which went up, or at least some of the colleagues in the workshop. But there are some very exciting dates as well, especially the Sentinel-1D. So yet another radar C-band satellite is going up later this year, or the other Sentinel family members, Sentinel-6B and Sentinel-5. So talking about Earth observation, I wanted to emphasize for all of you, and again, if you are already using Earth observation data or you are thinking to use, these are the ones what I'm showing on this slide, which you should really consider. So Sentinel-1 and Sentinel-2, they are really, really the workhorses anywhere in the world, basically. And these are free and open data. Sentinel-1 is looking at you're using radar, so it's an active sensor. They were sent up at 14, as I said earlier, 2016, 2024. And one more is going up, hopefully this year. And the Sentinel-2, which is an optical satellite, is a passive sensor, went up 14, 15, and 2024 again. And one more is going up, I think, either this year or next year. So these are the two, well, not two satellites, 2 satellite families which are flying. But of course, if you look at the numbers in the middle, you see there are some issues. So if you are familiar with data storage, you can immediately notice that the amount of data we are generating from these satellites, it's the best way to describe it is huge. So it's a lot of data coming daily from these satellites, 20 terabyte about. And through our different dissemination ways, we basically disseminated so far over 800 petabyte of data. So we are talking about really an overwhelming amount of data. So you have to be very smart when you want to use these systems. And I'll get back to how to actually run this or use this data in a second. But before I go there, Sven, the Geogram director, already mentioned some of the satellites which are coming up and can be very crucial for agricultural monitoring, including, crop area estimation, crop yield estimation, which are, I understand, most of the webinar participants are interested. So I would emphasize the LSTM, the CHIME, and the ROSE-L missions here. Those 3 are definitely connected to agriculture. Land surface, the LSTM is a land surface temperature monitoring mission. So think about actual land surface temperature, but also derived evapotranspiration. And this comes back also to water resources management, of course. Some countries, this is really serious. I assume also here in South America, if I think about Chile, Argentina, but even the southern part of Brazil, I assume, as far as I understood, water resources are limited. The CHIME and the Copernicus Hyperspectra mission, the main thing here to know is that since it's a hyperspectral mission, it will be very useful to derive soil properties, crop health. And again, the GeoGam director in the previous presentation mentioned that one threat which is really strongly coming up is pests and diseases. So this satellite or the data from there will be extremely useful to monitor crop health. And then we have a rose L, so it's an L-band radar, which is a little bit different, basically detecting vegetation on Earth is very useful, especially in those areas, those tropical areas where you have cloud cover. So cloud cover does not really bother the radar systems. I can also mention here Sentinel-1C, which are currently flying, if you remember. And the L-band radar will be able to, you will be able to use it for really discriminating different crop or plant communities. So for example, palms will be easily detected or discriminated with the L-band radar. But I don't want to go too much into details here. So these are also going up to add even more data to those which already exist. But don't worry, you have a few more years. So this is 2028, 29 when these will be going up. And I already talk a lot about the Sentinel-1 and 2 series or families. These are flying currently. But as I said earlier, when I just started, that these are what we call operational missions. So here as a long-term assurance of data coming. So as a National Statistical Office, most of you, I understand from there, want to really invest in an Earth observation-based methodology, Earth observation data-based methodology. You can be assured that these data sets are coming continuously. It's not like you invest into something which will stop coming free and open in the next day. So what I'm trying to say here is the Sentinel-1 NG, NG stands for next generation, Sentinel-2 NG are already in the pipeline. So once the regular or the original set of Sentinel-1 and Sentinel-2 satellites finish their lifetime, which will be in the 2030s, these satellites, kind of the replacement of them, will be already flying. And the financing or budget are all approved for this. Again, don't spend too much time, already mentioned the numbers, very big, huge numbers. So you have to be careful also when you plan your daily Earth observation data-based activities. But there are some solutions, actually relatively simple solutions. Once you pass the technological solutions, you will have actually a relatively easy way to work with the data. I want to mention two things here. One is when you have a local so-called high-performance computer, and I understood that many statistical offices do have it. I think Maria, you mentioned that you guys have a high performance computing center, for example. So once you have a center like this, you can use this center or the computer itself basically to analyze, crunch the data what you get from the Earth observation part. So of course, when the data is coming from the satellites, it's really just data, ones and zeros basically. But at the end, these high performance computing centers will allow you to easily manipulate the data for your needs. I'm just showing one example of what we have at where I work at, if you remember in Esrin, Rome, Italy. So we have a high performance computing center, which are incoming scientists, students, projects can use. So this is one kind of solution if you have a high performance computing. And the other type of solution, of course, if you have some sort of cloud-based ecosystem. So what we did in Europe, based on European Commission and ESA budget, is what we call a Copernicus data space ecosystem. So here we push all this data, what I was talking until now, in there in the near real-time basis. So basically, you have one Sentinel-2 image, and it will be there, within 5 hours or next day. Honestly, I don't know the latency times, but very soon that data will be there, and you can access it through cloud access. So CDS is a cloud-based platform. Of course, there are others. This is also a commercial solution. So anyone can use the data. And the beauty here is that the data is there. So you don't have to pay for the data storage itself. More like if you want to use some sort of algorithms to, get some sort of results what you need, then you pay for the processing time. So there is the data access. You can look at it already. You can sign up. This is absolutely free until you start to crunch some numbers. So these are the two options. So HPC-based, local, high-performance computing-based systems, and a cloud solution. And I will show two of my projects, which both use this one of the other or the other solutions. So I will talk about Syria, which is a global crop type mapping project, which ESA funded. And I will talk about San4Stat, which is more focusing on working with statistical offices on yield estimation and crop acreage estimation at a national level. You will always see who are the implementing partners of ESA. So these are usually companies or universities from ESA member states. So World Serial, what we do here. So basically, the magic question or questions are where food crop production taking place in the globe, which crop is grown, and when, basically. We had a third question about irrigation. I will not go too much into irrigation here, but you see some of the outputs from the World Syria project. So basically, they are in a very simplistic way, because we also have a talk later today or tomorrow on the details of the system. So I will not gonna go into details. But basically what we did here is to use this satellite data, what we provide from Sentinel-1 and Sentinel-2 to detect certain crops anywhere in the globe at 10 meters spatial resolution. So we built a system which can run, as I just showed earlier, either on an HPC or in a web-based, so cloud-based platform. The cloud-based platform is basically ready. You can already look at it, use it. I will show an example on that as well. And the HPC-based platform is also coming. So just zoom into a little bit of the outputs. So you have a system. You say, I want to have a temporary crop land extent, crop or cropland extent anywhere in the world. If you say, I want it in Brazil, I want it in Bolivia, or I want in within Brazil, only in Rio Grande do Sul, you can have it through the system with generally very good accuracy numbers. In the first phase, as you see, we have having two phases. The first finished in 2023. We basically proved the concept that this is possible. So we did crop land, crop type, and irrigation mapping anywhere, or actually everywhere in the globe. In crop-wise, that time we used basically cereals and maize. And now in phase 2, we went several steps forward. So basically, the system, well, already, but definitely in a very, very near future, we'll be able to generate crop type maps anywhere in the world seasonally. So it's not like once in a year, it's more like based on the seasons. And you see the crops there, up to 11. Of course, for South America, maize and soybean, I think the two really biggest ones. But I guess even some of the others are important for you as well. What we do, how the whole thing works. Again, I'm not going to go into it because a colleague who is really behind the system will talk either today or tomorrow. But very briefly, we have field data collection. We have some sort of an algorithm based on the growing seasons. And eventually, you have a crop type map as an output. And this is how the system looks like. It's basically just a website. You can go there. You have the links already to discover and see what is possible, what you can do in terms of looking at already created products, or if you want to create your own product. As I said, you want it for Minas Gerais in Brazil, you go, you say, this is what I want. And after a few basic steps, actually, you have an output. And we are trying two different things in terms of the system runs, and I think this is very important for the statistical offices, and it comes back to basically this so-called field data collection. Now, what I'm talking here, and you, if you are not familiar, I'm not sure who is in the audience. Point is that in many times, especially if you are talking about national food security, national food security estimation, many times the data is sensitive. So you don't necessarily want to share data out to the, you know, to the whole world on your especially on your ground data, meaning X and Y, where I grow maize, where I grow soybean, and so on. So what we do, we have a basic model in WordSeria where you don't have to share any data. We have our own data, and the system can give you a crop type map, whatever you want. You see the default models there. And we have another option when you can use one of the cloud systems, or the cloud system or the HPC system. And you can, in addition to our training data, you can use your own agency data. And with that, your own agency data, we don't get the share, so we don't get the data. You keep it in your you know, basically within house, but you can pre-train, not only using the pre-trained system, but you can improve any kind of output from the system because you are adding extra training data into it. I have to be a little bit fast, but I think this is the fastest way to explain. But I am happy to follow up if you have questions or more details you want to hear on this. Finally, basically, we are also doing some use cases, and for you might be interesting the Brazil case where we work with COMAB and INPE, and we are looking into wheat yield estimation, generally in Brazil. And we have a lot of trainings, a lot of materials. So if you are interested in the system, please, the presentation will be shared with Maria, and she will share it with the others. You will find all kind of links here. And basically, this is the WordSeria. And now we have Sen4Stat, which will also be explained with another colleague later, either today or tomorrow. So I will just go on the large scale here. But as the slide says, we are developing yet another open source toolbox using free and open Earth observation data to improve agricultural statistics. And this is at either it could be a parcel or definitely at the census level, which is again coming back to you audience, the National Statistical Offices. So this is very important, what we do here. So using these good old Sentinel-1 and 2 data sets has some sort of a processing, which was developed in, well, not at ESA, but with the implementing partners. And the system is being tried with several national statistical offices already. So we have several keywords here in the bottom of the slide: cost efficiency, statistical granularity, statistical timeliness, sampling design, survey, and data quality, and downstream applications. So we are trying to overview all this to make sure that national statistical offices, how to put it, can be happy to have a system which provides really timely, relevant, and very accurate data for your reporting needs. So basically, we use, as I said, mainly Sentinel-1 and Sentinel-2. We have 5 automated product types. You see them, cloud-free imagery for your area, time series, crop type maps, crop growth condition matrices, and crop yield estimation. And this is basically one of the most important part here. So this, we could even think in, especially 1, 2, 3, on just the underlying data what we use within this system. So look into individually, and but not to spend too much time. So we have the cost efficiency part where we look at accuracies coming out from our data sets. And what you can see here is a comparison between when you only use your own ground collected statistical offices data sets and when you use these data sets in collaboration with remote sensing data. Again, don't forget, remote sensing data is free and open. And I am showing here a system which is also free and open. So you just have to learn the system and you can run it locally. And you will reduce, of course, the famous term here, the amplitude, and you reduce the sampling error. And you can see the comparison here. I don't have a p-values here, so if it's statistically different or not, but you can see the sampling error down from 2.47 to 0.94, for example. Sorry, I don't see the side here because I have a little pop-up window. Anyway, second case, the statistical granularity and the statistical timeliness, similarly to the previous one. Of course, the magic here is really reducing the error of the estimation in particular in acreage in Spain. So barley, to be exact, so it's a cereal. And basically, again, the proof here is that using Earth observation data will reduce your error to those zones when you can confidentially report your results to your upper management or to the agricultural ministry or whatever you deal with. I showed some examples here from Spain, but it's not only Spain at all. You will see at the really last slide, but generally what I can say is actually we are focusing mainly on non-European countries. So Spain was just one part which we dealt with, but mainly we work with outside countries. So one other example on statistical timeliness is Pakistan, where, of course, the statistical agency of one of their states asked for a timely statistics because of their reporting needs. And we did this for rice area estimation, as you can see. Then again, irrigation a little bit from Spain, but I would rather want to focus on the sampling design for the Philippines. So it's not a European country, but it's very important is that the system and the Earth observation data what we use can consider the statistical sampling design which each National Statistical Office uses. So you know it better than me. Many statistical offices have different sampling designs, and the system would consider that when using it of generating acreage of different crops and, of course, yield estimation. And again, I have to emphasize also the different crops here. So unless, I mean, not how is in the World Syria where you have a set of 10, 11 crops. Here in Sanforstat, since we are looking at national level or even within national territory, so a county, a state if it's a federal country, here the importance is that all the crops which are in that area can be mapped well as far as Earth observation data is useful there. So it's not necessarily 10 crops, but the World Syria offers, and that's of course only a mapping exercise. Here you can detect all the crops which are feasible with Earth observation data, way beyond those 11 classes what we use or crops we use in World Syria. Then survey and data. So as I said earlier, we use statistical survey data for acreage estimation, but keep in mind that you need less field data if you use Earth observation, or if you have the same amount of data, almost guaranteed that you will get a better, more accurate output in this case for acreage estimation, a map, if only you would use statistical methods. And then I arrive to the last slide. So as I said, just to show that we are not really focusing on Europe here. So we implemented the Sanforstat system in 6 countries. I should have said in the first slide that this is in very, very close collaboration with FAO, and especially Lorenzo, who introduced the webinar, or who actually made all this webinar basically available. So we work with FAO quite a bit, and in collaboration with them, we always look for countries where we can support national statistical offices' efforts. As you see, Africa quite a bit, but also in Asia, we have a presence, a little bit in Central and South America, but we hope to broaden this effort. So we are very happy to work with any of the statistical offices here. So there is we are not singling out any countries. And yeah, please talk with Lorenzo, talk with me to see the opportunities how to implement the Sem4Stat system. I close here. Thank you very much for your attention. Any question now or later, I'm here, happy to be engaged. Thank you very much.
Thank you very much, Zolt, for the amazing presentation. It was like super inspiring to see everything the European Space Agency is doing, and not just the satellite systems, the technological capabilities, the Copernicus data space, but also how all that valuable data and functionalities are made free, are made open, and like easy to access. The World Cereal Project is really like stood out because food and water security is such a relevant issue, especially for our region here in Latin America and the Caribbean, and the possibility of the NSOs like generating their custom products using the pre-trained world serial models is like very, very valuable. Also the open source tool, the Sem4Stat, all of them are extremely valuable information for the NSOs. And at the end, I think you are going to share the presentation, the slides with us, and they will be available in the Hub website so that participants can access all of the links you are showing. And thank you very much. And before going,
if I can jump in just with one sentence, Maria, thank you for the nice words. So we are putting really a lot of effort to work with third parties. I mean, in this case, national statistical offices, especially in the agricultural domain. I already mentioned to the in-person participants that we are organizing a meeting in Rome next year in March, April, March, February, somewhere there, and I will give more info as soon as I have on statistics, how to use Earth observation data on statistics, any kind. So from agriculture to biodiversity and anything in between. So I will share that data once we have the details with you, Maria, and with the whole group through you. And anyone is very welcome to join these meetings. Thank you very much again.
Okay, thank you. Please share with us and we can like reshare to all our community. Thank you very much. And also, before going to the next presenter, we know that we have participants join from many different places around Latin America, Caribbean, and around the world. And we would love to get to know the participants better. So please take a moment to write in the chat your country and the name of your institution. It will be great to see where everyone is connecting from. And we can like go to our next presenter, which is Mr. Christoph Van Trich. Are you here, Christoph?
Yes, I am.
Oh, great. Please, let's welcome Mr. Christoph. He is the senior research at Vitor Remote Sensing in Belgium, where he specialized in agricultural applications with a focus on both global and local agriculture monitoring. He leveraged advanced remote sensing technologies to address food security challenges. His work spans the development and deployment of crop mapping and monitoring algorithms. His research projects cover a wide spectrum from regional farming studies to large-scale initiatives like the ASA World Cereal Project that Mr. Zoltan has showed us, always aiming to bridge the gap between cutting-edge machine learning technologies, the reality of large-scale operationalization, and the science of remote sensing. Dr. Christoph, you are welcome, and the floor is yours.
Thank you very much, Maria, for the introduction. Very happy to be here. Let me share some slides in case you don't see them. Feel free to interrupt me. I only have one screen, so just let me know. Okay, perfect. So yes, I have the honor to talk a bit more about supervised crop type mapping with remote sensing, with a specific emphasis on the World Cereal System, which was nicely introduced in general by Zoltan already. So that really helps before going a bit into more detail. So just very briefly, indeed, I am from working at the Vito Remote Sensing, which is a research and technology organization in Belgium. And we are leading the, there is a bit of a delay here, but we are leading the consortium that does the World Cereal work, funded by World Cereal, by ESA, as presented by Zoltan. And so, yeah, as the general overview has already been presented, I can dive a little bit more into detail on what this system now is actually doing. And so it's really important to understand, sorry if there is a little bit of duplication with what Zoltan presented, but I think it will be fine. But it's really important to understand that World Cereal is both a product as well as a system. Many people have heard about World Cereal in terms of the first global crop type maps of maize and cereals. And this is also what the aim of the first part of the project was, to produce and show the feasibility of producing crop type maps at the global scale with the satellite remote sensing. So that was quite a success, although many things remained to be to further research and improved. And that's why indeed that the second part of the project now really dives more into exposing the system and making it more user-friendly towards all kinds of stakeholders and end users. And so today we're going to talk about bit more about the system itself, because that allows you really to create your own crop type maps and also improve the system locally by adding potentially your own private data that you might have in your country. So yeah, what this system allows you to do is really creating crop type maps in a relatively fast way. So at the moment, the default is still that it runs near the end of the season. So it looks at a full growing season to then identify what crop has grown there. It's true that for some agricultural applications, this is not yet enough. And we know that there is a big demand to also support in-season crop type mapping, which is even more challenging. That might be on the roadmap, but for World Cereal, the situation is now that this is an end-of-season crop type mapping system that gives you an overview of the agricultural landscape of the past season. And so there's many different use cases. Just one example here where we activated and expanded even the system during the first part of the project to enable rapid assessment of area changes in agricultural landscapes, in this case in the conflict areas in Ukraine, to really quickly get an idea of what crops were still being grown in the war zone, and to really have an objective view on how the agricultural landscape was actually impacted by the conflict. That's just one use case, but there's obviously an endless amount of cases that can be investigated with automated crop type mapping. Now, how do you do actually crop type mapping? you actually need quite a few components. So it's not just a model that you're able to apply to any region. No, you really need a couple of modules that work closely together to really bring to an end user something that nicely works together and brings everything from the domain together to really present you the state of the art of crop type mapping from space. That starts already in the upper left with the reference data, which is really a massive database. Sven already mentioned it in the GeoGlam presentation. This is really a massive database of whatever public data that we can collect, and that really allows us to learn to teach the algorithms to recognize crop types from space. It also allows you to put your private data there and to keep it private, but this is really an essential component. I mean, it's called supervised classification because we really need to teach the models to recognize the crops based on some examples from the actual in the field. This can be farmer declarations in Europe or in situ campaigns. With windshield surveys where people are recording geolocation and crop type that's growing at a specific moment in time. All this data is compiled in this massive database that is actually our training point to teach the models. Then we have the actual processing module where we train the models and where we also have the entire system that is able to, once trained, also apply them to a new region and to produce the crop type maps, and then finally to make everything accessible. We also have a visualization and dissemination module that exposes not only the default products, but also allows you to interact with the system in a very user-friendly way. This slide was already briefly shown by Zoltan. So how do you map crops from space? Yeah, there is no single algorithm yet that can always work without ever needing to be trained on examples of actual crop types in the field. So the first step is still to have some field data, either new field data or historic field data. Once you have that, then you look for matching observations from satellite time series. Sentinel-1, Sentinel-2 are the most important ones for us. We also look at meteorological data, precipitation and temperature time series, and some other descriptors like altitude, slope, and location. And we match those two, so what is actually growing in the field at a certain moment in time and what the satellite sees around that period. And that is being used to train a crop identification model that learns to match. And then for a new location, just looks at the satellite observations and the meteorological time series, and then predicts what is the most likely crop that was actually growing there. And so once trained, that runs in an end-to-end way, hopefully in an efficient way, and produces for a new location a crop type map. And so that first part is already usually one of the largest challenges. So if you always have to start from scratch and always have to go back to a field, do a field campaign, that's quite labor intensive. So that's why we have put a lot of emphasis on that first module, that reference data module that GeoGlam already presented there as well. So this is really a massive effort. And I think, Sven, that your screenshot was actually more up to date. So the one here only has 87 collections, while at the moment we're already at 142, and a massive extra ingest is currently happening. So this is really where all kinds of data sets that anyone has ever collected that we could find and that these institutes or people agreed that we could share with the public, they can be found there in a harmonized way, which means that from maybe the local language of a certain crop, that is harmonized into a common harmonized legend of crop types so that everything is consistent everywhere. And that data is then being used to train our models, but that data can also be explored by you for your own purposes as well. And then interestingly, it also allows you to upload your own data sets and then make use of all that harmonization effort that we have done. So there is an AI assisted module there that actually proposes the translation from your local labels in the field to our harmonized legend, and then allows you to correct any mistakes that might have happened there. Then you choose by default that data is just kept private. You can only use it. So you are able to use all the public data sets and in addition your own private data set, or you can share the data set with the World Serial team so that the global models can be improved, or you can also make them public so that the data set itself can also be redistributed to the community. But the default, as Zoltan already mentioned, is that your data remains yours and it's kept private so that only you can use it to tailor the crop type maps in your region to your data. There is an entire course, a massive online course that we launched a few months ago. Just on this reference data module, it teaches you how a proper field campaign should be organized, what is the essential information that we need to make that observation useful to train crop type models, and how to ingest it in the end in this reference data module. So if you're interested in that kind of activity, then definitely go check out this course that will walk you through all of that. Then, of course, one of the most important parts is the actual backbone model that does the classification, or at least is able to understand all these different time series and data streams that come in from the satellite and need to be translated into something useful that says something about what is actually growing there. And as you can imagine, with every 5 days an overpass of Sentinel-2, in a year time, there is a lot of data, of which many observations are not even saying anything about what happens on the field. It's a cloud, it's a shadow. There is maybe nothing growing on the field at that point in time. There is different atmospheric conditions and so on. So there is a lot of noise and just a little bit of signal. And the idea is really that a model needs to be strong to isolate the signal that is relevant for your task, which is to identify the crops. And for this, we now have this quite innovative geospatial foundation model called Presto, which is developed by the colleagues from NASA Harvest. They have done the research work behind that, and we actually met at the moment when we were entering the new stage where we could refactor some of our backbone algorithms, and they had a use case. Well, just the research part was done, and then we joined forces and we actually integrated that model into the World Serial pipelines. And what this now does is that it has this model that is able to digest all that information that comes in from Sentinel-1, Sentinel-2, Meteo, all this information, really tons of data, and it summarizes everything in just 128 features, which is really much smaller than what comes in originally from the satellite. This is a model that was pre-trained already, so it has already learned to discard almost all of the noise that is not relevant. And the idea is that when you want to train the algorithm or fine-tune it for crop type recognition, that you need much less labels of crop types in the field to get to meaningful predictions if you would compare it to something that has to learn from scratch and first needs to distinguish noise from signal. So that part has already been done, and we've done quite some analysis and comparisons already, and we do see that this is really a powerful approach and really puts much more power at the user fingertips to, with limited amount of data, still get to nice results. So what comes out of that, as I mentioned, is just a summary of all the satellite and other inputs into a very small set of highly informative features. These features are not your crop type map yet, so this is just the basis for classifying the actual crops, but we're sure that this contains the actual useful information and not all the other parts that is not really relevant. And you can then benefit from what has been learned already in the past and adapt, if you want to, the model to your needs based on your data. So what decisions then still need to be made? And I was listening carefully to what Zoltan said, and I need to make a very small correction, because World Serial has its default models, and soon we'll have an update where we offer these 11 crop types out of the box. So in principle, you can generate anywhere without feeding any training data, a crop type map based on these 11 crop types. But in principle, if you go through the system as it is now, that trains also the last part of the model, then you can basically choose whatever crop type that you want, as long as there is training data available in the neighborhood of your area you want to map. And that training data that is available is either the public data, if it coincides with your region of interest, and potentially augmented with your own private data that you have uploaded to the reference data module. But say that you want to map strawberries, which would be very difficult class to map, but okay, so it's not part of the 11 crops. But if you have enough training data for that, you are definitely able to pick that crop as well and to train the algorithm to identify strawberry as well. So you can pick any class that that the system, well, that your training data supports. And then the other thing, of course, that you also need to choose is what season to map the crops for. I have here. Okay. So how is this flexibility presented to you? For example, here you would be in a Python notebook, which may be or may not be familiar to some of you. But yeah, we like to suggest to you when the major growing seasons in the region are, but we also know that often local experts know much better what the seasonality is. So you can basically pick whatever season processing time that you want. The idea is that you nicely center the processing period around the crop season that you want to map. And then you also get presented with a crop type picker, which just lists all the crops that were found in the training data, and then you can basically pick them yourself. We do have quite some recommendations for that, so we always advise users to aim for at least 100 samples, training samples per class that you want to map. If you go below that, then it becomes a really small class and really difficult to map them. You can use hierarchical grouping, or you should use hierarchical grouping. Our crop type picker also presents you that to organize the smaller but similar classes into broader, more meaningful categories. So say if you only have 25 cotton and 5 flax samples, then it might be better to just map fiber crops instead of going into the cotton and flax details. So this kind of flexibility, you have that to stop at certain major crop groups, especially if the crops below that are very similar in the eyes of the satellite, and if you have only limited amounts of training samples available. So always be very cautious about treating very similar classes separately. We know that everyone wants to distinguish between some potato varieties maybe, but yeah, if it looks from a satellite point of view really the same in the growing season, if these are planted at the same moment, harvested at the same moment, and behave kind of similar, then it's really going to be extremely difficult from 750 kilometers altitude to see the difference between the two. So yeah, you need to have some sort of sense of reality and not have too big expectations if it cannot be seen from space. Okay, and then choosing the season, of course, yeah, we use a processing time of a year. So a year of satellite data goes into the model, but obviously in some regions there is more than one, there's two, sometimes even three seasons, or there's just one big season, and it depends a bit on the farmer. So it really is also important that you tell the model, like, okay, where in this year is my season actually located? And so with our date slider, you are really invited to make sure that the season you are interested in is nicely centered in the middle. We are still looking to improve that and make that even more user friendly in the future, but at the moment this is just the reality. Center the processing period nicely around the growing season you want to map, and that is the best way to tell the model what season you are interested in. Then importantly, adding your own data, like I mentioned, it's not strictly needed. You can just map the crops that are available from the available training data. Or just use the default models without any specific training. But we have done some tests, and we really want to offer that always as a motivation, that adding local data really significantly improves the classification accuracy. And that doesn't have to be a lot of data. We see that in some cases, or in average cases, adding just 50 samples already improves the performance 28% towards the potential maximum improvement that you would get with endless amount of training data. With 500 samples, you already get to 63% of the potential improvement. So with limited samples, you can already boost the classification accuracy quite a lot. And also, very importantly, quality is more important than quantity. We prefer just few samples of the whole agricultural landscape, which are very good in thematic and positional accuracy, rather than having a massive data sets of thousands of samples, of which maybe 30% is wrongly positioned. Maybe the point is on the roads instead of on the fields. maybe some labels were not correctly recorded. This kind of noise really hurts the model. So it's really important to just stick to quality and not go to quantity. Okay, and once everything is there, then we enable the entire thing that happens under the hood. So in red is basically the red rectangles identify where you as a user have flexibility. So the public data is what it is. We add to that constantly. We have a pre-trained Presto model that gives you the opportunity to benefit from everything that has been learned already in the past. Then you optionally can add your own private data, but you don't have to. And then what you can do is pick your crops, pick your season, train a very lightweight model on top of both the public and potentially your private data. That crop type model then gets uploaded to the cloud in the cloud-based system. And then with one click, you can launch a workflow that will generate your crop type map. What happens under the hood itself, the default cloud where we at the moment run on is the Copernicus data space ecosystem, like Zoltan already mentioned. So this takes care of everything of directly connecting to the official archives of Sentinel-1, Sentinel-2, our meteorological data from Agera 5 reanalysis, the Copernicus DEM. So the data loading is taken care of, the pre-processing, which is cloud masking, temporal aggregation, everything is done automatically. Then the Presto model comes in, it summarizes all that data into these 128 features. Your model or the default model gets applied on top of that, and then you get the crop type map with the classes that you as a user have picked. If you do that in our Jupyter notebooks, you have full flexibility to train these models and pick the crops and so on. If you just want some more exploration, then you can, as Zoltan already showed, also just visit our World Serial Processing Hub, which is still a quite new thing that we launched only recently. This is still quite basic at the moment and just allows you to launch the default models of crop no crop versus crop type. And especially crop type, it's only limited amount of crops. And we also have to say that this is still an older model, so it will get an update in the next few months, probably by the end of the summer. And also very soon, you will be able to actually plug in that model that you trained yourself so that you can basically use that model once and for all in the processing hub to very conveniently generate crop type maps with your model. So yeah, this I already mentioned. So you can also use the hub to download the official products from 2021. But as we can imagine, much more interesting for you is to generate the custom products and monitor how that is going. So yeah, basically you can pick your entry point into our ecosystem depending on your needs and also your technical skill level, how willing you are to dive into some more interactivity with the code. So at the most accessible level but least flexibility is just exploration of the products. Some more flexibility but requires some more interaction are the World Serial processes in the processing hub. And then if you want full flexibility, you can dive into the Jupyter notebooks or even in the GitHub code repository. Everything is open source, so feel free to dive in there and let us know if you find any issues or if you have any requests. So for the time being, not so much is needed. All you need to run the thing in the cloud is a CDSE account. It comes with free credits, which are every month replenished. This is funded by European Space Agency. And then, yeah, if you need more, then additional credits can always be purchased. You can go to the World Serial GitHub. And if you want to use the notebooks but don't want to set up a Python environment or something like that, then you can also use a Terrascope account, which just gives you access to the notebooks without the need to install anything. If you go to the GitHub, then you will find nice buttons that immediately bring you to these notebooks on Terrascope, where you can create an account and explore this without any further obligation. Okay, just to finish up, some expectation management. So yeah, the custom model, if you train your model, then also the responsibility goes to you. And so it can only be as good as the available training data. We don't do, if you keep your data private, we also cannot intervene and do curation and data quality checks. So the model can only be as good as the training data that you upload to the system. Should you wish to share the data, at least with us to improve the default models, then we will actually take some effort into helping you curate some data. We will check, do some basic quality checks, but yeah, the default is it's your data. We don't see it. So yeah, please keep in mind that then the results will depend heavily on the quality of the data that you have put in there. As I mentioned, current default models will get an update in a few months from now. So don't judge the actual accuracy of the map that comes out of the default models if you haven't retrained them yourself right now, because so far it has been a proof of concept, and now we're working on these final models that will also be used to produce a new global round of World Serial products early next year. Every job needs to load the original data from the Sentinel archive, so be patient. It takes a little bit of time. It's quite a heavy process to load a year of satellite data, process everything, run a model, and produce a map. So just be a little bit patient. At the moment, very large scale processing is still limited. So you need to inform us if you want to do that right now. Although in the next few weeks, we're going to launch another update that will automatically split a large extent and allows you with much more ease of use to process larger extents as well. Of course, that comes with a higher credit usage, so you have to keep an eye on that as well. What will come up in the next few months as well is the ability not only to train your own crop type model, but also to customize the crop length model. So at the moment, crop length for us is defined as temporary crops. Perennials are not in there, but we want to allow you to also retrain the cropland model to make up your own definition and to say this for us is now the definition of cropland, so that you can also play with that. Then expansion of the processing hub, giving you more flexibility, is also coming up. We are constantly increasing the availability of the public reference data, but this goes in batches, and there is a massive batch upcoming in the next few weeks, which will suddenly expose many more data sets to train the model on. We'll add these 11 crop types, which are currently not all supported yet in the default models. So that's also still upcoming. And then, yeah, hierarchical crop classification, won't go into detail here now, and increase the efficiency of the jobs to make them a bit faster, a little bit more cheaper, but definitely also put some more effort into the scalability so that you can more easily also generate larger scale maps. So yeah, we have a lot of outreach activities going from promotional packages that you'll find, webinars that we organize, MOOCs, of which the first one has been launched, up to all technical trainings. So keep an eye on the developments. We share our updates on LinkedIn. We have all our videos, recordings on YouTube, and we have also a mailing list. So if you want to be updated on all the new developments, then I would definitely invite you to subscribe there. That's it. I'm going to stop here. Thanks.
Thank you very much, Christoph. Thank you for sharing more details about this so rich ecosystem and such an important initiative like the World Serial Project, and also for walking us through some of the technical aspects, the methodologies, some useful advice, general recommendations for those who want to work with it. And also for showing us a little of what happens in the background and for what's going to still is coming. We can see there's a lot to happen in the next months from this work. Thank you very much.
You're welcome.
And I asked people to write in the chat the place they are coming from, just to make a brief review. We have a lot of people from Brazil, from IBGE, from all of the states. We have also people from other institutions from Brazil and from other countries, like Fiocruz in Brazil, people from the Ministry of Agriculture and Food and Security and in Belize. We have people from in Costa Rica, from Chile, from Peru, Colombia, from Dani. In Brazil, we have people from Embrapa. We have people from a lot of places. I'm very happy to see that we can reach so many people from so different institutions, not only NSOs. And oh, that's it. Everything is in the chat. People from also from universities. Thank you. Thank you for being here. We'll make a 10-minute break. And in continuation, we have two presenters. We come back at 10:50 in 10 minutes. And we are coming back with Eduardo Vasquez from INERI. And the other presenter is from IBGE, is Ian Nunes. So we come back in a few minutes, okay? Just for a coffee, for some water, and we'll be back. Hello, everyone. Can we go to our next presenter? So let's welcome Mr. Eduardo Vasquez, which is the Deputy Director of Coverage and Special Analysis at the National Institute of Statistics and Geography of Mexico, the INEGI, where he's responsible for remote sensing projects related to agriculture. Since 2013, he is the member of the work team on Earth observations in the North American Tripartite Committee on Agricultural Statistics. And since 2021, he is the co-chair at the Joint Task Team of UN-CEBD and UN-CEBD on Earth observations for agricultural statistics. We have the pleasure also to have him with us this week in Rio de Janeiro. So, Eduardo, thank you for being here, and the floor is yours.
Thank you, Maria. Thank you for your kind introduction. Thank you for hosting the workshop. It has been a very good week working with the handbook and also in the presenting in this webinar. Okay, thank you. Good morning, everyone. I will let me share my screen. Oops. Can you see the presentation?
Yes, we can see.
Okay.
Yes, perfect.
Okay, thank you. Well, I will tell you today about the works that INEGI has done for the definition of an agricultural frontier using Earth observations in Mexico. I will tell you about the first works developed. Also, we will see the agricultural frontier concept, some background, the statement of the problem, the methodology used in the first processes, our first results, and also the last processing developed, and the review of the last processing, the findings, and also a new approach to improve the results, the advances of the new works developed, and the next steps under development. Finally, the preliminary conclusions. Well, I will begin with the agricultural frontier concept. The agricultural frontier concept is the whole areas dedicated to the agricultural activity in Mexico and on all the country, but also that areas cultivated and not cultivated, but have been used for crops in the last 5 years. This is a concept that is commonly used in CEAP and INEGI. CEAP is an institution that depends on the Agricultural Ministry, and this is a common concept in both institutions. And the idea is to have the map of these areas as a frame for future surveys or events dedicated for agriculture. Well, some backgrounds. As a result of the 2007 agricultural census, Mexico get a shapefile of all census lands with a primary activity identified. I mean, agricultural, livestock, or forestry included as an attribute. This information was updated by other projects. The most important was the update of the agricultural census framework that was conducted on 2016. And the result of this updated was the label. All the land plots were labeled with the main activity. The statement of the problem was how to produce timely and cost-effective and reliable estimates of the national agricultural frontier using air observations combined with artificial intelligence algorithms. For that, the objective was calibrate an algorithm using an artificial intelligence and Sentinel-2 satellite imagery to estimate the national agricultural frontier. This is a collaborative work between two offices at INEGI, the Data Sciences Laboratory, that is the area that has all the infrastructure. I mean, hardware and software to run all the processes of big data, AI, and machine learning algorithms. And also by the coverage and special analysis area that is part of the field operations for agricultural and economical censuses and surveys, that we are responsible for the in situ data that were used in the exercises that I will show you. Also, not only for in situ data, also for the review of the results and analysis, and to feedback our colleagues of the Data Sciences Laboratory. The methodology used in the first words is presented in this slide. We had all the land plots of the census labeled, with identified with agriculture and non-agricultural areas. But also we had Sentinel-2 images processed to obtain the geomedians, and also from the geomedians, our colleagues of Data Sciences Laboratory get 48 texture filters, 20 spectral indices, different spectral indices, and also they obtained a segmentation of the whole country to integrate the polygons with the pixels of same characteristics. With all this information, we get a stack of 80 raster layers. You can imagine the amount of information, 17.2 terabytes. And using the plots labeled, it was constructed a table, a future table, with 832 descriptor variables. With this information, the models were trained. There were used 3 different models, algorithms, extra trees, random forest, and multi-layer perception. And as you can see in this slide, random forest got the best results, the best accuracy. And for validation, there were two ways to validate information, nationally and locally. Local validation got the best results. And we got a map. In this slide, you can see the different exercises generated in the process. The first exercises were conducted using Landsat imagery, and the last ones using Sentinel-2. The first ones allows us to fix some situations and to calibrate better the process. Always we use the update of the agricultural census frame 2016 as a base for compare the different results, and you can see how the different processes were closer to the reference data. This is the map of the results, of the last results. You can see here as higher classifier certainty is less surface, and as the certainty is lower, we have a higher surface. Besides this exercise, our colleagues of the data sciences laboratory, we agreed with them to run another process, a final process, using images corresponding with the period of the agricultural census 2022 conducted in Mexico, by INEGI in Mexico, that covers from October 2021 to September 2022. Those results were reviewed to identify areas with good and poor algorithm performance, but also to make some feedback to refine the algorithm from the results of the review. In this slide, you can see the last exercise conducted by our colleagues of Data Sciences Laboratory. There were two processes aligned with the dry period and rainy season that correspond with the autumn-winter season of crop growing, and the spring-summer that corresponds with rainy season of crop growing. You can see more green areas in the rainy seasons because of the effect of the humidity on the water in the whole country. Those processes were reviewed visually by the coverage and spatial analysis area to find how the algorithm was performing. In many cases, we can show that the algorithm has a good performance. This is the dry season of an agricultural zone. And this is the rainy season for the same zone. You can see that the image show and correspond quite well with the results of the algorithm. However, in some other zones, we can show that the dry season show big areas covered by cropped zones. This is the rainy season for the same area. But when we see the image, we can detect that only some spaces are dedicated for agriculture. The rest of the area corresponds with hills and mountains, and so this is a confusion area where the algorithm has big confusions. In this other area, we see the result of the dry season process compared with the rainy season, but you can see that it's a fully mountain area. Here we have just deciduous trees or bushes, but not really cropped areas. And we find other places dedicated to agricultural activities, where the dry season results show a good correspondence. Also the rainy season, but you can see that the algorithm couldn't identify some spaces well defined as an agricultural activity. Well, the findings of this visual review are that the confusions identified by the algorithm in the results reflect that our labels of land uses as field true were not as adequate as previously thought. That's because the labels were applied to the entire plots. Meanwhile, pixels inside the plots were not homogeneous. I mean, inside the plot, sometimes are the house of the farmer or some installations, or simply tree fences surrounding the plots. In addition, the labels were assigned in 2016, and we have 6 years apart from the last processes carried out. So it was necessary to have a new labels for training polygons. However, to have a world country, national-wide country of labels would take a too long time to have it. So a new approach a new way to approach the problem and of labels and image processing was discussed with our colleagues of data sciences laboratory. And we agreed that taking into account that the processes of the whole country were developed using a grid that covers the entire country, we select specific cells of this grid with different conditions. And the north side of the country is the desertic part of the country. The center of the country is more related with the cropped areas. And the south part of the country, we can find a jungle, but also some areas dedicated to agriculture. After the selection of the representative cells, we obtained the geomedian of the Sentinel-2. We agreed to focus the process only in the winter-autumn cycle because it's the dry period, and we agreed that to avoid the confusion of the algorithm with the excess of the humidity and growth of natural vegetation. For each cell, we digitize training polygons finer than the limits of the lands. And so we define these 5 classes: agricultural zone annual, agricultural planted perennial, agricultural not zone, protected agriculture, and not agricultural. These are some examples of training polygons for each class: agricultural, perennial, protected agriculture. Sorry, not this. Class 3 not zone, protected agriculture, and non-agriculture, different kinds of non-agricultural zones. With these 5 classes, our colleagues of Data Science Laboratory ran a classification process that also was reviewed. This is the first review. You can see the amount of the training polygons that were used in this first process. And the inputs for this classification were the 12 bands of the Sentinel-2 and also 2 spectral indices, the EBI and NDVI, normalizes difference built-up index. And the classifications were carried out using 3 sources: a segmented images, gridded image of 5 by 5 pixels, and the original geomedian image by pixel. In this slide, we can see the results of each classification. We have some examples. The first one is the original image in false colors infrared, pixel result, segmentation result, and the grid result. Using different areas, this is a well-defined agricultural area. We can see that segmentation and grid has a poor results. If we see this other example, we have the same thing. Segmentation and grid had poor results compared with the pixel classification. Other part of this segment process, you can see that the grid processing confused the planted or seeded area with non-planted. So as a result of this review, we saw that the best result was obtained from the pixel classification, and we tried adding new inputs for the classification. We add texture filters, and this is the result adding texture filters. With the texture filter, we can show that some confusions, the algorithm had some confusions for the results. So without texture, we got the best results. For that reason, we decide not to use texture filters in the next processes. But also we saw that it was necessary to refine the training polygons to improve the results. This is a comparison of the original processing training polygons with no texture and the refined training polygons. We increased the amount of training polygons in this refining processing, and the results were better than the original ones. We can show a better separation of the cropped area from not cropped area but agricultural area, and also some confusion of the original process were more controlled. This is another example where the agricultural area is not has not crops in this moment of the image, and we can see that the result identify very well non-cropped and cropped areas. Also for zones without crops, some confusion were controlled. And this is other example of one area of with no cropped areas, but dedicated for agriculture. We get better results with the refined polygons, but the refinement was continued, including a reclass of some polygons. Also, we added in the next step, we added bare soil index and also the digital elevation model. In this table, you can see that the process with the bare soil index did not improve the results. And the basic classification with the digital elevation model, I will show you the comparison. This slide, we can see the original image, the previous classification, basic, and basic with DAM. We can see that too much areas seeded were better represented in the basic with DEM. Also for those areas non-related with agriculture were better defined. In this area with high plots related with agriculture, seeded and not seeded or planted, we got a better definition using the basic plus the DEM. So even when we got better results, there are some places where the algorithm has some confusions, but we think that the basic classification plus the DEM is better than the last ones. We got also other processes, including more refinement of the training polygons. That improved the results. Also, for other cells, so this part of the Mexico place, where perennial areas are more common, were well identified. We can see this part is perennial crops area. Well, the next step on the development, as a result of the cells analyzed, shown that the training base has allowed to obtain satisfactory results, we will use the training polygons to process the 8 adjacent cells and evaluate results. And also for the classification with acceptable results, we run a post-classification process to generalize its isolated pixels. And also we will test the generation of a segment-level classification from pixel classified images, enhancing the segmentation process. We will process the adjacent, and once we get good enough results, we can move to process next level of adjacent cells, and so on until we can have a national process. For the segmentation improvement, we are looking for the best combination of variables to get a better result. We have made some tests, but I'm not to stop too much in these images because this is ongoing work that we are review and evaluating. As a preliminary conclusions, the new approach is working. We are advancing step by step, validating visually results before doing the next movement. There is still too much work to do before a national processing. First, get the results for the adjacent cells, and also obtain the parameters, the best parameters to generate the best segmentation. Meanwhile, the team of the coverage and spatial analysis of field operation is learning about the Python, Jupyter notebook, and machine learning methods, apps, and libraries, because our colleagues of data sciences laboratory is sharing with us all those information. But also data sciences laboratory is strengthening its knowledge of crop development and spectral responses of perennial and annual crops derived from the review that we are doing, and we are sharing and feedback with them. This collaborative work is enriching the process. We know that it's still too much work to do to get the final or the complete process of the national to obtain the agricultural frontier, but we think that we are in the right line, in the right path. Well, this is all for my side. Thank you. If you have questions, I'll be glad to respond to you.
Thank you very much, Eduardo, like for walking us through how you used EO in such a like a major operation like the Mexico agriculture census. And it was really interesting to hear not just about the methodology, but also some of the results and details of the algorithm and how different techniques provide different results, and also the decisions you had to take based on it. For our audience, sharing this kind of like hands-on experience is very useful, very helpful for understanding the real-world challenges of applying these models in something as complex as a census. Thank you very much.
Thank you, Maria.
Thank you, and particularly for us at IBGE that we are planning our next agriculture and livestock census for 2026. It was very, very important to see. And our next presenter, our next and last presenter today, Ian Monteiro Nunes. His work is totally related to the agriculture census. Ian, it's a very good pleasure to have you here representing the IBGE. Ian Monteiro is a data science leader with over 25 years of experience, specializing in agricultural statistics and innovation. At IBGE, he leads a high-impact data intelligence project, advancing remote sensing, computer vision, and optimization. And with almost a decade of data science research and a background in neural networks, his experience spans startups, research, and leadership, managing high-performance teams and developing data-driven solutions across multiple industries. Ian holds a PhD and a master's in data science, driving technological advancements in his field. Thank you very much for being with us, Ian, and the floor is yours.
Thank you, Maria. Can you see my screen?
Yes.
Okay, thank you. So good morning, everyone. Thank you again for the introduction. And my name is Ian. And now, since last year, I lead some data science initiatives at IBGE focusing on agricultural statistics. It's an honor to speak at this event. And I hope our experience can contribute to the discussion of the use of Earth observation to support production of official statistics. I'll do my best to give you a small overview of the field boundary delineation project we are working on. Okay. So a little over 1 year ago, in May of 2024, we set up a challenging goal to develop the necessary data science tools to support the census planning, and not only the census planning, but the production of agricultural statistics at IBGE. And for today's agenda, I will walk you through some of the progress we've made and how we are planning to do in the next months and the next year. Well, the first task that we decided, here, I lost on a slide. So the first task we decided to attack was field boundary delineation. But why field boundary delineation? This is our base task. Why it's our base task? Because we think that a good field boundary delineation result can improve the crop mapping results in the future. Not only that, we can support the census planning by understanding and identifying new areas of agricultural activity in Brazil. We can use the field boundary delineation during the collection to georeference the production. We can also calculate and compute the potential agricultural area to support and help assess certain sustainable development goals indicators. We started last year, as I said, but in the first approach was to use public available data set. But we do not have public available data set for Brazilian territory, specifically for this task for field boundary delineation. We have just small data sets with very, very limited data and very limited time frame in the past. So after some tests and some transfer learning tests, we decided that realized that we need to produce a proprietary data set. And since last August, we are doing that. Actually, we now have 24 states of Brazil, 24 out of 27 states of Brazil, IBGE's agencies involved in this project, in this collaborative project. And we are now, today, we are capable of producing about 150,000 parcels per month. And it's a very hard task because Brazil is very big, and we have to represent the entire, the most diversity that we can, especially in the most productive areas of Brazil. So we are trying to span these efforts across the entire territory, leveraging the choice of that cities to represent diverse landscapes, biomes, agricultural holding sites, because Brazil has about 4 million small familiar agricultural holdings. So we have to represent as well as the agribusiness. And as you can see in the image, it's not as regular as it is in many places. The agricultural holdings and the plots in Brazil are not square-shaped plots like we saw in Europe or in the United States. And the size of and the size of the plots are a very good challenge to tackle. And to do that, not only and to do that, we choose a supervised learning, as I said before, since we are producing the labels. And we are using Sentinel-2 Planet. I didn't put in the image, but we are also using the elevation model and some kind of preprocessed data of time series, because for the field boundary delineation, we do not use time series images. We use images from 1 or 2 months at most. And we used as well AI for boundaries, FAST's public data sets, and our proprietary data sets. This gave our model some diversity and the fine-tuning in our data set. We pre-train our model in the AI for boundaries and FASTs and fine-tuning in our proprietary data set. It improved a lot the results. We understand that this task, this field boundary delineation task, is not a segmentation task, only a segmentation task. It's an instance segmentation task. So we tested lots of different networks from YOLO, BizNet, UNet, using different tasks and different approaches and different data modeling, trying to tackle the task the best way. In the end, HRNet with a specific data modeling performed better. So we are using now HRNet, which is a multi-resolution convolutional neural network with a specific attention module called object contextual representation, pre-trained using a novel self-supervised learning method that we developed using superpixels. And this strategy improved a lot the results we were having last year. As experimental setup, I can say that now we are using 62 cities for the SSL representational learning, unsupervised representational learning, and 24 cities, labeled cities for the fine-tuning and testing. We also performed ablation studies, as I said before, with different networks, different training strategies, different data modeling for the task, actually binary task, multi-class, object identifying, instance segmentation, semantic segmentation, panoptic segmentation. We tried lots of things to find the model that the network and the method in a whole that better suited our task. Here I'll show you some results, and it's interesting how just a second, and you can see how the results are for different regions of Brazil right now. This is a prediction for a city called Brejo Alegre at São Paulo. Here, in the second square is the labeled, manually labeled plots. And here's the prediction. In the next slide, I'll show you if it changes. Okay. A comparison, because we have to have a starting point. And I'm not sure if all of you are aware of, but there is a global project called Global Fields ID, VARDA. And they claim that they have plots for the entire world with high quality results. So VARDA was our baseline. because we have to understand if we can do a better job than Varda to Brazilian territory, also if it's worth developing our own model. And here I'm showing you in the back, in the lowest part of the slide, the table of the results, and you can see that our model outperforms Varda by a lot in all cities that we tested. It's a spoiler, but in this image specifically, and in the other ones that I will show, it will be the same structure. The manually annotated plots is the second square, and Varda predictions. The error in the Varda predictions in yellow in the third spot, and the second line are different predictions of our models. Observing that yellowish areas and these ones here are errors. So you can see that Varda has a spread error and our method has a concentrated error in the lower area of the image. It's pretty much the same across the Brazil. Actually, Varda, which are our baseline, has a very poor performance at Caatinga bioma, which is mainly the northeast region of Brazil, and some other areas as well. Minas Gerais, it is very challenging for Varda as well. And you can see that the results are much better again at Okara in Ceará state. Varda misses lots of plots in the north of the city, and we miss some plots in the south of the city. But that's the difference between them. So the less yellowish these four are, the better the projections were. And even in Okara, that we do not perform a very, very good job, we performed a much better job than the Varda projection. There are some places that are much easier, like this one, Taquaral in São Paulo. But even in that places, we performed better than Varda. So that's the main results we have until now for the field boundary delineation project. And we are expanding because today we are training with only 24 cities for fine tuning. We expect to train with 100 cities in a whole bunch of more areas of Brazil in the next months, and we will include. I didn't say that these results that we are showing are using only Sentinel-2 images. We are preparing to use planet scope images with much higher resolution, spatial resolution, which we believe that will improve our main challenge, that is the smallest plots with less than 20,000 square meters. This is the main focus of our errors. So if you can see, if you in the borders of the city, the most errors are in this kind of plots, the smaller ones. So we believe that using planet scope images will be able to improve the results in this kind of areas. And how are we going to use? We are going to use the plots in the next census. We are planning to do the census into 2026, and we are going to offer the enumerator the plots to collect data from each agricultural holding, collecting which crop was cultivated in each plot, georeferencing the entire production of Brazil, at least at the places that we were able to produce good quality plots. we are going to combine the plot boundaries with crop information and production data after the census. And this will enable us to have probably the most comprehensive public agricultural data set for tropical regions, with production data, area data, even with production strategy or production managing used by each of the farmers. This will be one of the greatest outputs of the next census. But we are not stopping with the field boundary delineation. We will also perform a crop mapping. But to perform a crop mapping, we had to understand how is the survey, how is the literature at this moment, to understand and trace our path to the next months and years. Because this project that we are working on will not end with the census. It will continue for supporting the agricultural official statistics. So we have to plan the next steps. And for the next steps, we started conducting a survey to determine that in which direction are we going to. So first, we propose the taxonomy for the main tasks that we are aiming to perform in the future, and understand what kind of technologies and which technologies are performed best for the individual tasks. This ends in a proposal of a novel crop mapping method called CITSIAM, based on CITSMOCO, which produces a competitive result with the state-of-the-art producer results of CITSBET, but with 20 times fewer parameters. So it's a much faster method. And for large-scale projects like a Brazilian project, we had to think of how can we scale up all of the methods that we are using and the methods that we are proposing. I didn't said before, but now we can, with the infrastructure that we already have, we are able to perform the field boundary delineation for the entire territory of Brazil in only 5 days, using Sentinel-2 images. If at the time we include planet scope, it will probably be slower, about 4 times slower, but it's still okay for Brazil. 15 to 20 days of processing time. It's not so long for Brazilian territory. We also proposed the lightweight pipeline crop time series parcel classification, pretty much similar with the ones that Christoph presented, but with a difference. Since we are assuming that we are going to use parcels, our pipeline uses parcels as the unit of classification for crop mapping. And this is the main difference. There are other differences in the method, in the modeling, in the losses, and how we are conducting and how we're presenting the method, but it's pretty much like Presto for self-supervised, for pre-training. And we actually concluded pretty much the same. With just a few labels, we can improve the result a lot, like just like Christoph said, about 50 new samples improved by 28%, according to him. We didn't have this kind of refined number, but we can show something like that with 0.1%. We go up from 64% with 1% of the data set, original data set, which is some thousands of samples. We go up to more than 70% and so on. This is already tested, and all the works that I'm showing here are submitted or published already. In the future, we intend actually to propose and support methods through the Brazilian Agricultural Sample Survey, supporting the dual frame sampling design with the remote sensing based data and the census data for the list frame. From the data of the census and from the sample survey, we hope that we have enough data to do crop yielding properly, both pre and post harvest crop productivity prediction. And we are very new at IBG. We just completed 1 year of project. And if someone last year told me that we are going to achieve so much in this just little time, I would probably say that they are being optimistic. But we achieved very good results, and we are very small team, a very collaborative team across many different regions in Brazil, many different teams in Brazil. There are people working with us from the other directories, from other states, from universities. We are building a research group, an applied research group, trying to get the best of the research and apply to real problems at IBG. So in the last year, we achieved some good results, in my opinion, actually, at least, that we proposed at least three different methods addressing the problems that we have with good quality results. Actually, top tier performance across the tests that we had performed in. Ending up in 5 papers already submitted or published, 4 abstracts accepted for international events, and 6 additional papers ongoing for the next 2 months. So we are working a lot, and I hope we are just gaining traction. We are just gaining momentum, and the next chapters will be great. I hope so. And that's it for now. Thank you a lot. I'm here to answer whatever question you have. Thank you. The floor is yours, Maria.
Thank you very much, Ian, for showing the so important work you have been conducting at IBGE. We are very proud of it, of having you as our representative. And now I would like to pass the floor maybe to Lorenzo if you want to say something, and to ask people if they want to include questions in the chat. We still have some minutes to answer.
Thank you very much, Maria, and thank you to the excellent and stellar presentations. This is really a moment where we want to have feedback from the participants. So I will really limit my comments just to say that we can clearly see from those use cases how Earth observation data, which is providing inputs, and artificial intelligence, which is providing the acceleration to extract from the data the information, it's serving real needs. So the last example from inputs, for instance, from Jan, is showing how we can detect the parcel boundaries. And I just want to, encourage the reflection on how useful it is for a country to be able to link the farmer identity with each plots. So this can allow for very key applications from the statistics. For instance, the area, the acreage that is associated with every farmer, but also for the rural policies, investments in subsidies. You can monitor, if you're a policymaker, how is your policy impacting? If I'm giving subsidy, I'm expecting to see an increase in yields, but if I don't have the plots explicitly mapped and linked to the beneficiary of the subsidy, it's very difficult to do that. So I think we can clearly see how those applications, they serve statistical purposes, but also policies and development. So I hope that questions can come on how to make this possible. What are the barriers? I think those are the finer details where the devil is hiding, is, what are the barriers to make this happen? Thank you.
Thank you, Lorenzo. So we don't have any question in the chat, so I think I'm going to say some words. Especially, I'd like to thank you, our excellent speakers and the participants that are here. It's our first webinar, which is like 3 hours long, and I'm very happy to see that the audience keeps with us, and it shows how important and rich and insightful the sessions were. Thank you. And before we close, I'd like to invite you to join us again tomorrow for day 2 of this technical webinar series. Tomorrow, we are going to focus on the statistical integration and advanced AI for IELTS forecasting. And building on today's discussions, we will explore how Earth observation data, statistical modeling, and AI can work together to improve the crop IELTS estimates. And we will have presentations from Sophie Bontemps on combining UN maps with regression models to estimate crop area. Claudia Stenner from IBGE, who will present the Global Geospatial Statistical Framework and its relevance for agricultural statistics. Also, Gilberto Câmara from INPE and UN-CEBD, with a live demonstration of AO data processing using the SITS framework. Also, Professor Zigal from Wuhan University, sharing global contributions to the EO handbook and practical use case. And finally, we'll conclude with a panel discussion on the path from EO data to actionable in statistical insights with Lorenzo De Simone. And for those who are from IBGE, we'll have a seminar in the afternoon at 3 p.m. So you are invited to connect with us. And we hope to see you again tomorrow at 9 a.m. And thank you, everyone, and see you soon. Bye-bye.
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 Thank you all.
Thank you.
Bye
Bye-bye.
bye. Bye.
Bye bye, guys.